Hello, universe explorers! Today, we're diving deep into one of the most astonishing astronomical discoveries of our time. The James Webb Space Telescope has recently uncovered what is believed to be one of the oldest galaxies ever seen, rewriting our understanding of the universe and its beginnings. So, strap in as we explore the depths of space and time through the eyes of this incredible technology. Have you ever wondered what secrets the universe still holds? Imagine embarking on a cosmic voyage that takes us back an astounding 14 billion years. Our story today circles around an extraordinary observer, the James Webb Telescope, whose recent revelations are causing a stir in the scientific community. In the vast, silent expanse of space, the James Webb Telescope, launched in December 2021, has been tirelessly working since opening its giant infrared eye to the cosmos. This marvel of technology has not just met expectations, it has shattered them, offering us views further into the depths of space than ever before. Picture this as a time machine journey to the dawn of the universe. Among its most baffling discoveries are numerous bright galaxies from these very early epochs. The sheer luminosity and mass of these galaxies pose a cosmic conundrum. According to our current understanding, there simply wasn't enough time since the beginning of the universe for such massive galaxies to form. To put this in perspective, imagine stepping into a land where toddlers are as hefty as teenagers. You'd certainly have questions. Is there something extraordinary nurturing them, or is it possible that your fundamental understanding of growth is flawed? This is the puzzle that astronomers are now facing. These massive, bright galaxies are challenging our theories of cosmic evolution. Could it be that our estimates of the universe's age are incorrect, or is there a mysterious piece of the cosmic puzzle that we're still missing? The James Webb's findings might just be the key to unlocking these mysteries. As we continue to peer deeper into space, each discovery refines or redefines our grasp of the universe. Could everything we know about the universe be wrong? As we dive deep into the cosmos with the James Webb Telescope, we find ourselves at a crossroads in cosmic history that challenges our most fundamental theories, including the Big Bang and general relativity itself. Since its launch, the James Webb Telescope has been peering into the universe's earliest chapters, reaching back to the first 500 million years after the Big Bang, a time when the universe was a mere infant in cosmic terms. However, the galaxies it's revealing are anything but infantile. These cosmic behemoths, mature and massive beyond our expectations, are turning our understanding of early galaxy formation on its head. Imagine looking at a photograph of your ancestors only to find them in modern attire and smartphones in hand. Startling, isn't it? That's akin to what astronomers are experiencing as they observe these advanced galaxies. They were supposed to be simple clusters of stars, slowly gathering mass over billions of years. Instead, we find them already well developed, which contradicts our existing models that predict a gradual assembly over a much longer span. As the James Webb continues to deliver new data, it's not just adding new pages to our cosmic storybook, it's demanding a complete rewrite. Each observation pushes the boundaries of what we thought possible and compels astronomers to rethink the very processes that form galaxies. Have you ever wished you could travel back in time? While science fiction teases us with time machines, the James Webb Space Telescope, JWST, is turning those fantasies into reality, at least when it comes to unraveling the mysteries of the cosmos. Our universe is roughly 14 billion years old, filled with stories of cosmic origins and evolutions. To understand these tales, we need more than just powerful telescopes. We need a time machine capable of looking back billions of years into the past. Enter the James Webb Space Telescope, an engineering marvel that sits on the boundary between science fiction and reality. This $10 billion instrument doesn't travel through time itself, but does something almost as magical. Using the well-established principle that light travels at a constant speed of about 300,000 kilometers per second, JWST captures light from galactic events that happened millions, even billions of years ago. Here on Earth, light's journey is instantaneous over small distances, but in the colossal expanses of space, light from a distant star takes years to reach us. Consider this. When you gaze at a star twinkling in the night sky, you are actually looking into the past. The light from that star began its journey years ago, and by the time it dances across your eyes, you are witnessing history. If that star ceased to exist today, its ancient light would continue its journey across the universe, reaching us just as if nothing had happened. The James Webb Space Telescope harnesses this principle to study the universe as it was in its infancy, providing unprecedented insights into how galaxies formed and evolved shortly after the Big Bang. This is not just about looking at stars. It's about reading the chapters of the cosmic storybook that were written long before humanity existed. What if you could look back in time and witness the birth of the universe? The James Webb Space Telescope, JWST, is our window to these ancient cosmic days, employing a fundamental principle that lets us see the universe as it existed billions of years ago. Imagine the light from a distant galaxy traveling across the endless void of space, journeying for millions, even billions of years before finally reaching us. This light acts as a messenger from the past, carrying secrets of a young universe. The farther away a celestial object is, the longer its light takes to reach us, and thus, the further back in time we look when we observe it. The JWST specializes in capturing this ancient light, particularly focusing on infrared rays. Infrared light, associated with heat, can travel vast distances without losing much of its intensity. This capability allows the JWST to peer into the most distant reaches of the universe, revealing objects and phenomena previously beyond our grasp. The telescope's design is a marvel in itself, tailored to detect these long wavelengths of light. Stationed far in space, equipped with sophisticated infrared technology, it opens up a panorama of the universe that is as awe-inspiring as it is invaluable to our understanding of cosmic evolution. Among its recent breakthroughs, the JWST has provided an extraordinarily detailed look at one of the earliest known galaxies, known as GZ9P3. This galaxy, observed at a redshift of 9.3, offers a glimpse nearly back to the origins of the universe itself. A redshift of this magnitude means we are observing this galaxy as it was over 13 billion years ago, less than a billion years after the Big Bang. Each new discovery by the James Webb pushes the boundaries of our knowledge and fills our cosmic map with data that was once thought unattainable. These glimpses into the distant past are not just expanding our understanding of how galaxies form and evolve. They are reshaping our entire conception of the universe. Just a few years ago, the galaxy known as GZ9P3 was nothing more than a single point of light when viewed through the Hubble Space Telescope. Fast forward to today, and thanks to the advanced capabilities of the James Webb Space Telescope, we are now able to observe this galaxy as it existed a mere 510 million years after the Big Bang, or roughly 13 billion years ago. What the team discovered next has added an intriguing layer to our understanding of the universe's youth. GZ9P3 is not just any early galaxy, it's an astronomical anomaly. This galaxy is significantly more massive and mature than we would expect for its place in the cosmic timeline. It already hosts several billion ion stars, a surprising revelation that adds complexity to our understanding of how galaxies evolve. The puzzle deepens with the realization that GZ9P3 is not merely an exception, but an extreme one. It is approximately 10 times more massive than other galaxies observed by James Webb from the same era. This discrepancy poses a significant challenge to our existing models of early galaxy formation. How could such a galaxy grow so massive so quickly? Kit Boyett, a team member and scientist at the University of Melbourne, reflected on this enigma in a publication for the Institute's Pursuit. His insights highlight not only the capabilities of the James Webb Space Telescope, but also the profound mysteries it helps us explore. As we delve deeper into the cosmos, each discovery, like GZ9P3, reshapes our understanding of the universe's formative years, prompting astronomers and theorists alike to revisit and revise their theories. GZ9P3 is not just an extraordinary galaxy due to its immense size and advanced maturity, it's also a cosmic detective story written in the stars. Thanks to the James Webb Space Telescope's advanced imaging capabilities, astronomers have unveiled that GZ9P3 has a complex, intriguing structure. It features two bright patches, each marking a dense nucleus. This is a clear sign that GZ9P3 likely formed from a dramatic event, the collision of two early galaxies in the nascent universe. This cosmic collision, still unfolding during the epoch captured by James Webb, offers a rare glimpse into galactic formation through mergers. Kit Boyett and his team observed that the morphology of GZ9P3, typical of two interacting galaxies, is still visible, indicating the merger is not yet complete. This ongoing fusion is a dance of destruction and creation, as the merging galaxies cast off some of their matter into the surrounding space. This discarded matter is not just debris. It is a clue that what we are observing might be one of the most distant mergers ever detected. The ability to discern such fine details in a galaxy so far away showcases the unprecedented power of the James Webb Space Telescope. Further analysis by Boyett and his colleagues has allowed them to delve into the stellar population within these colliding galaxies. Young stars, typically brighter and more energetic than their older counterparts, illuminate these galactic images, providing insights into the star formation processes occurring within this ancient merger. Especially for those galaxies so distant that their light has traveled across the cosmos for billions of years, uncovering their secrets becomes a true challenge. Take, for example, GZ9P3. Within this galaxy, a young and vibrant star population, sparked by a recent galactic merger and less than a few million years old, outshines the older stars, which have been glowing for over 100 million years. To navigate this stellar luminosity battle, the GLASS collaboration employed a combination of direct imaging and spectroscopic observations. Spectroscopy is a powerful tool that allows scientists to determine the chemical composition of stars, differentiating between the young and old by their elemental makeup. Younger stars, still in their early stages of life, are predominantly composed of hydrogen, with traces of helium reflecting their nascent state. In contrast, older stars tell a tale of cosmic alchemy. Having exhausted the abundant hydrogen in their cores, these stars have fused it into helium, which in turn has been transformed into heavier elements, or what astronomers refer to as metals. These metals include silicon, carbon, and iron, the latter being one of the heaviest elements that stars can synthesize before their spectacular demise in supernovae. By focusing on these specific elements, the research team was able to probe the ancient stellar population within GZ9P3. The James Webb Space Telescope, with its unparalleled sensitivity, detected these metals, offering a glimpse into the life cycles of stars that have long since ended their nuclear journey. This not only enriches our understanding of stellar evolution, but also enhances our comprehension of galactic ancestry and the environmental conditions that prevailed billions of years ago. With each observation, the James Webb Space Telescope peels back layers of cosmic history, revealing the intricate dance of galaxies and stars. When the stars of GZ9P3 ended their lives in cataclysmic supernova explosions, they did more than just light up the cosmos. They enriched the early universe with metals. These metals, dispersed through the galaxy, became the essential building blocks for the next generation of stars, fostering a cycle of stellar birth and rebirth. The revelations from GZ9P3 have also given us startling new insights into the size of its ancient stellar population, which was much larger than previously expected. This suggests that galaxies may have reached chemical maturity much more rapidly than we once thought, with a swift and efficient buildup of stars and metals occurring soon after the Big Bang. These discoveries underscore the significance of galactic mergers in cosmic evolution. While isolated galaxies slowly churn out stars until their gas and dust are depleted, galaxies that are close enough to feel each other's gravitational pull undergo a more dynamic process. As these galaxies draw together and eventually collide, they trigger a fresh inflow of gas, catalyzing new periods of star formation. This galactic dance, marked by collisions and mergers, not only speeds up star formation, but can also rejuvenate it even after the original galaxy's star-forming materials have been exhausted. This process explains how massive galaxies like GZ9P3, containing several billion stars, could appear so early in the universe's history, much earlier than previously expected. The universe, it seems, is a grand stage of continual creation and destruction, with each galactic encounter sparking new life. Rapid star birth, also known as a starburst, is a dramatic event, and galactic mergers are a prime catalyst for such bursts of creation. This phenomenon offers galaxies a fast track to expand their stellar populations. It turns out that most of the large galaxies we know, including our own Milky Way, have grown significantly through this very process. Take the Milky Way, for example. It has a history marked by the absorption of smaller satellite galaxies that once orbited it. Currently, our galaxy produces stars at a somewhat sluggish pace. However, this is set to change dramatically. In about 4.5 billion years, the Milky Way is predicted to collide with the Andromeda Galaxy. This monumental event will trigger a massive inflow of gas, sparking a new, vibrant era of starburst activity. The observations of GZ9P3 have been a game-changer, revealing that this pathway for rapid mass accumulation and star formation was even more significant in the early universe than previously anticipated. Kit Boyer and his team's work has shown us that galaxies were capable of amassing mass at an astonishing rate through mergers. With star formation, the James Webb Space Telescope has unveiled new mysteries. It has also provided answers that reshape our understanding of cosmic evolution. One of the latest revelations from the James Webb Space Telescope is a collection of ancient galaxies that significantly impacted the universe when it was less than 1 billion years old. An international team discovered that these galaxies, which resemble today's dwarf galaxies, played a crucial role during a pivotal stage of cosmic evolution between 500 and 900 million years after the Big Bang. These smaller galaxies were far more numerous than their larger counterparts in the early universe. Scientists believe they supplied most of the energy necessary for a process known as cosmic reionization. This process was essential for the growth and development of the universe, effectively reshaping it on a grand scale. As Hakim Ach, the lead researcher and an astronomer at the Institut d'Astrophysique de Paris, explained, "We're really talking about the global transformation of the entire universe. The most surprising aspect of this discovery is the critical role played by these small galaxies. Despite their size, they were instrumental in the reionization process, fundamentally altering the universe's structure and behavior. Imagine a time when the universe was shrouded in darkness. This period, known as the epoch of recombination, occurred around 380 million years after the Big Bang. For the first 380 million years, the universe was a dense, ultra-hot environment where free electrons endlessly bounced around particles of light called photons, making the cosmos opaque and dark. But then, a dramatic transformation took place. As the universe expanded and cooled, electrons began to bond with protons, forming the first atoms of hydrogen, the simplest and lightest element in the cosmos. This process marked the end of the universe's dark age, as the free electrons that had previously scattered photons were now bound up in neutral hydrogen atoms. Suddenly, light was free to travel across the universe, rendering it transparent for the first time. This first light, known as the cosmic microwave background, CMB, is a cosmic fossil that uniformly fills the universe. It provides a snapshot of the infant universe, offering clues to its early conditions and evolution. Fast forward to the era of cosmic reionization, occurring between 500 and 900 million years after the Big Bang. It was during this critical phase that the faint yet powerful galaxies discovered by the James Webb Space Telescope played their transformative role. These small galaxies, with their cumulative radiation, had the power to reionize the universe. Their energetic output supplied the necessary radiation to strip electrons from hydrogen atoms, making the universe once again transparent to ultraviolet light and ending the cosmic dark ages. Welcome to Blasovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blasovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q&A sessions with experts. Your membership will grant you the chance to participate in live Q&A sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos, and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together, we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comments.